My name is Daniel Manuel, and this is my 1601 glider presentation. The glider name is the reverse swept glider, and in this project we did design, build, and test a glider to fly in a competition within our own class. The glider must be able to fit in a 16 by 16 inch box, and its successful flight must be over 20 feet. The glider must be hand thrown and land intact, and it should be primarily constructed out of the materials provided. To measure success, this glider has to fly a minimum of 20 feet. Design alternatives 1. Wing shape and wing design. I had the option of a reverse swept, airfoil, and dihedral for the wing shape and design. The pros of the reverse swept is that this wing shape is proven to be more stable, but the con is it limits the speed that the glider can be thrown at and possibly reduces distance. For the airfoil shape, additional lift is generated when compared to a flat plate airfoil due to the difference in pressure on the top and bottom of the airfoil. But the con is it might not make a difference on such a small scale glider. For the dihedral, it adds stability, but the con is manufacturing a dihedral may be done inaccurately, which would negate the stability that would add if one side is at a greater or lesser angle. For design alternatives 2, we had adhesives. CA glue, wood glue, and masking tape were our options. The pros for CA glue is that it cures fast, which makes it easier to set a part at the right angle. But the con is if a part is set at the wrong angle, there's little time to correct it. For wood glue, the pro is if a mistake is made, it is far easier to correct than when using CA. But the con, the part that is being joined together has to sit in that position for a much longer time before any test flight can be made. Masking tape. Pros is that it provides structure to the weak points without adding much mass, and can be used to level the roll of the plane. The con is that it should not be used as the only method to attach parts. Design alternatives 3, tail configuration and structure. T-tail, H-tail, and additional structure is what we have. The pros for a T-tail is that it's simple to manufacture, but the cons, it may be easier to stall if the horizontal is not set at the correct angle. For the H-tail, the pros are it has better roll stability when compared to the T-tail, but the con is manufacturing is more difficult, particularly in terms of symmetry of the tail. And additional structure. It strengthens the weak points of the glider, such as the nose, tail, and wing mount, but it adds an additional weight that would reduce the glide distance. Which alternatives have the highest probability of success? For wing shape and design, the reverse swept wing and airfoil shape together have the highest success. The increased stability that the wing shape would add, as well as the additional lift from the airfoil, are attributes that would perform well in the final glider design. The dihedral adds in stability, but the risk of not being able to accurately measure the dihedral angle may prevent the glider from flying straight. In terms of the tail design, the T-tail offers adequate roll stability and easier manufacturing than the H-tail, and the adhesives used will be CA and tape, due to CA's strength and ease in assembling the glider with the correct angles due to its quick cure. Tape will also be used to reinforce the joints with the most stress, and additional structures will be added to reinforce those areas as well. In terms of sizing, to size the glider, we used the size constraint that was taken into account. The wingspan was set to the maximum size of 16 inches to maximize the lift generated and give the wing a higher aspect ratio. The vertical stabilizer was sized by trial and error. With the first iteration's test flight, the glider immediately pitched up after release. So the vertical stabilizer height was reduced to make the horizontal stabilizer lower on the T-tail. And the fuselage was sized with research claiming that the fuselage should be 4 to 6 times the chord length. And with a chord length of 3 inches, I decided to make the fuselage 15 inches long. The original concept was to use the whole balsa stick that was given, but shave down the part leading from the trailing edge to the tail. The concept featured increased weight in the nose by using the full 1/4 inch width of the provided wood. The airfoil shape was a flat plate with a 0-degree angle of attack and a 7.5-degree dihedral. The stability came from the reverse swept wing shape. Roll due to the wings not being mounted perfectly caused the glider to veer during the test flights. So small increments of masking tape under the wings add a way to correct that issue. With the testing in the AMS, the glider would fly about 60 feet indoors if the glider was properly balanced and the center of gravity was on the quarter chord. Design iterations. In the second iteration of the plane, a cambered airfoil shape was added. The fuselage was decreased in size. The wing mounting point included added structure to prevent from coming off on landing, and the nose was strengthened with sheets of thicker balsa cut in a way to minimize drag. Having a cambered airfoil shape rather than a flat plate airfoil increased the lift generated from the first to the second iteration. The added structure strengthened the weak points that appeared throughout the testing, and with the tail spar, tape was added around the length of it to give further strength without adding much weight that the balsa would. In the final design, I have the cambered airfoil shape to generate more lift, reverse swept wings for added stability, a CG directly under the quarter cord. I have added struts under the wing to provide structure to wing mounting locations, a strengthened nose, tail spar strengthened by masking tape. This is my best test flight right here. Overall, the second design iteration added on to the performance of the first. Several weak points were targeted and addressed, such as the tail spar, which had the problem of snapping off. The airfoil shape added to the second iteration's increased glideability. The furthest test flight at 41.5 feet is what was on the right. The estimated CL is 0.0833, and the CD is 0.0008. In conclusion, the glider does meet their size requirement. It is made of mainly the materials provided, and it did not break on landing. And it met the distance requirement of 20 feet by going 23 feet. So it did meet the final requirements. If I were to improve the glider, I would use a material other than balsa for the tail spar. Most of the problems in testing came from the tail spar snapping off and having to repair with CA glue. Another issue was that the mast in the front of the glider during test flight would move, so a built-in adjustable mast would have been made test flights easier. A greater angle of attack could possibly be better. As I tested my final iteration, I noticed less lift, so to correct for this issue, I reduced the weight of the glider or I increased the angle of attack. And here are my resources. Thank you.